Hello everyone, myself Dr. Santimay Kundu. I welcome you all to this lecture of soft computing technique. This is the first lecture of module 2. Till now, we have covered module 1. In module 1, we have seen fuzzy sets, membership functions, basic operations. This class we learn about fuzzy relation. So to discuss the fuzzy relation, it is better to discuss relation on creep sets. So first try to understand the creep relation defined over two creep sets. So let A is a creep set. So A and B are two creep sets. A and B are two creep sets. These are two creep sets. A cross B is known as Cartesian product. So relation R is subset of this Cartesian product A cross. Here get an ordered pair which is A, B, where A belongs to the set A and B belongs to the set B. So here there is some point that A Cartesian product B is not equal to B cross A. Second is that the cardinal number of Cartesian product A cross B is equal to the cardinal number of A into the cardinal number of B. So this is the Cripps relation defined over two creep sets. Let's take one example. So example is, let's take A equal to the set, take it 1, 2, 3. B is a set, let's take it 2, 3, 4. So the Cartesian product, the A cross B, that should be equal to the 1, 2, 1, 3, 1, 4, 2, 2, 2, 3, 2, 4, 3, 2, 3, 3, 3, 4. Check cardinal number of set A is 3, cardinal number of set B it is 3, so cardinal number of B is 3 into 3, that is 9. So let's relation R which is equal to R, the relation R AB, where 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 A equal to B and AB belongs to A cross B. So A is related to B is the relation R. We can write A equal to B. So here we will get R equal to the element which are A and B are equal. So it is 2, 2 and 3, 3. 2, 2 and 3, 3. So we have seen that relation R is a subset of A cross B. So in matrix form, if you want to write it, we will get that the one row, the A1, 2, 3, it belongs to this, you can check row. 2, 3, 4 it belongs to the column. So 1, 2, 3. So relation is only this is 1, 2 is not present, so it is 0. 1, 3 is not present, it is 0. 1, 4 is not present, it is 0. In the relation 2, 2 is present, so it is 1. 2, 3 is not present, so it is 0. 2, 4 is not present, so it is also 0. 3, 2 is also not present, so you can write it at a 0. 3, 3 is present, so it is 1. 3, 4 is not present, so it is 0. So 1, 1 and 0. So what I want to say, in the Cripps relation, entries are either 1 or 0. So elements of the matrix of the relation are either 0 or 1. So try to define the union of the relations. So assume Rxy and Sxy are two relations defined over two Krebs sets A A and B, where X belongs to A and Y belongs to B. So we are defined two Krebs relations Rxy and Sxy. So the union of these two relations, we can check that Rsy union Sxy is equal to the maximum of the elements Rxy. Is Rxy and Sxy. So the union Rxy and the two relation Rxy and Sxy is the maximum of Rxy and Sxy. Similarly, the intersections of Rxy and Sxy is equal to the minimum of Rxy and Sxy. The complement Rxy is equal to 1 minus Rxy. Similarly, complement of Sxy equal to 1 minus Sxy. So, which is, so our entry should be either 1 or 0. So let R is a relations which is 0, 1, 0, 0. 0, 0, 1, 0. 0, 0, 1. And here it is 0, 0, and so only there are three elements. So let S is a relation which is 1, 0, 0, it is 0, 1, 0, 0, it is 0, 0, 1, 0, and 0, 0, 1. So try to find the union of these two relations. We try to find union Rxy union Sxy. So maximum of the elements. So first is 0, 1. So that should be your 1. Second maximum 1. These two are 0. This is 0. This is 1. This is also 1. This is 0. This is 0. This is 1. This is 0. This is 0. This is 1, 1. Next is 0, 0. So you can check that is the union. Similarly, if you try to find R xy intersection sx, so that should be the minimum. So minimum is 0, minimum is 0, minimum is 0, 0. Also minimum 0, minimum 0, minimum 0, 0. So you can write the complement of is 1 minus Rxy. So here you will get 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. So this is the example of the union, intersection, complement of Krebs relations. R is a relation R defined as xy, where x belongs to some set A and y belongs to some set B. So define a relation S which is YZ where Y belongs to B and Z belongs to C. So the composition relation, suppose it is T, can be written as R compose S. So that is the relation XZ where X belongs to, where you can check that XY belongs to R and YZ belongs to S for to B. So T, the composition, that we can say the relation T equal to R compose X is the relation can be written as XZ where XY belongs to R and YZ belongs to X. YZ belongs to X for all Y belongs to P. So let's try to understand one max mean compositions. So max mean composition, again we write the same, find the minimum element of XY and YZ for all Y, then ultimately find the maximum. So X is equal to 135, Y is also equal to 135. So R is a relation which is defined as XY where Y equal to X plus 2. S is a relation which is defined on the set XY where X is less than Y. So we are represent this relation on matrix. So R is equal to, R you can write both 135, here also 135. So Y equal to X plus 2. So for 1 it is 3. So least will be 0. For 3 it is 5. So least will be 0. For 5 no 1. So this is basically R. Now what is S? S also same thing. Row is 135. Column is also 135. So here X less than 1. So Y will be greater than X. So 1 is not present. Or 3 1 not present. 3 3 not present. 3 5 will be present. For 5 no one is present. So now we need to find the max mean T equal to, like a matrix multiplication. So first is that you compare first row and first column. So first row, again try to understand first row, first column, 0 0 0. So compare between these two. So minimum is 0 0 0. So this is first row, first column, this is 0. Similarly, first row, second column, first row and second column. So this is also 0. Now first row, third column. So 0 1 0. This is 0 1 0. So minimum is 0. Then minimum is 1. Then minimum is 0. So maximum is 1. So that should be the 1. So in this way we can find the max mean relation. If now next is everything will be 0. Now try to understand the Cartesian product of two fuzzy sets. In the Cartesian product of crisp sets, here the elements are, so with one fuzzy set, you know fuzzy set is an ordered pair. So let S is a fuzzy set, that is the ordered pair, which is x1 0.2, x2 0.4, x3 0.6, x4 0.8, b that is x1 0.1, x2 0.3, x3 0.5, x4 0.7. So Cartesian product of A cross B can be written as minimum of mu A x and mu B y, right? If it is y, then you can write y. So here it is minimum of that. So here the entries you can write x1, x2, x3, x4, same element here x1, x2, x3, x4. So this belongs to row and these are belongs to column. Now minimum of 0.2 and 0.1. So 0.1. Minimum of 0.4 now x1. So minimum of 0.1 and 0.2. The minimum is 0.2. Minimum 0.2 and 0.5. 0.2. 0.2, 0.7, 0.2. 0.4 and 0.1. So it is 0.1. Again it is 0.3. It is 0.4, it is 0.4, it is again 0.1, 0.3, you can check it is 0.6 x3, now it is 0.6, now it is 0.1, 0.3, 0.5 and 0.7. So this is the Cartesian product. Take one example. So small example, try to solve here. Solve these things. Here A is a fuzzy set which is A1 0.2, A2 0.7, A3 0.4 and B 0.5, B2 0.6. So if you check it here, you will get A cross B is equal to, so here it is A1, A2, A3, B1, B2. So A1 and B1 you will say minimum is 0.2, then A1 and B2 minimum is 0.2, then A2 A2 and B1 0.5, 0.6, then you will get 0.4, A3 0.4. So this is the Cartesian product of two fuzzy sets. So relation over a fuzzy sets, the membership values in a fuzzy relation indicate the strength of the relation. Again, relation is a subset of the Cartesian product of two fuzzy sets. So here we can check the relation is a Cartesian product of two fuzzy sets. So let's try to understand one simple example. Relation are defined as approximately equal, approximately equal on set x which is equal to 4, 5, 6. So we are defining 1 if x equal to y, it is 0.8 if mod of x minus 1 equal to 1, equal to 0.4 if mod of x minus y equal to 2. So 4, 5, 6. So here is r is, you can write 4, 5, 6. Here also 4, 5, 6. So 4 is equal to x equal to y, for this 4 equal to 4. Now 4 minus 5 is 1, so it is 0.8. 4 minus 6 is 2, so it is 0.4. Now 5 minus 4 is 1, so it is 0.8. 5 equal to 5, 1. 6 minus 5 is also 0.8. Now 6 minus 4 is 2, so it is 0.4. 6 minus 5 is 1, so it is 0.4. So it is 0.8. 6 equal to 6, so it is 1. So that is a fuzzy relation. So try to understand here the entries are belongs to So every value lies where is the Krebs relation? Where is the Krebs relations that, but in fuzzy relations, the element the Krebs relations. Fuzzy relation and the Krebs relations. Present the fever, corona, viral, corona, viral. Let Y denotes the symptom. So which is dry cough and muscle pain. Define the strength between the tuples X and Y. Between the tuples X and Y. Between the tuples. So this is tuples. So this is the X viral, then cold, and these are the symptoms. And these are the symptoms. So tricaf is tricaf is not, pain is also there 0.8. So viral maybe little more cough is there, temperature is also high, and this is the muscle pain 0.7, cold, so there will be more dry cough 9.4, temperature may be little less, muscle pain may be little. This is the fuzzy relation. Now operation on fuzzy relations. So same as the Krebs, so operations on fuzzy relations. So we are defined two relations on A cross B. So union of these two relations R and S on AB is maximum of mu R AB and mu S AB. So this is the union. Similarly, intersection is mu R S AB. This is equal to minimum of mu R AB mu S AB. Complement is that, suppose complement of mu R AB, this is 1 minus mu R AB. So max mean, so that is equal to maximum of an R1 on X cross Y and R2 on Y cross Z. So max mean composition, you can write R1, max mean composition, R1 compose R2 is XZ, where XZ belongs to maximum Y, minimum of is the maximum of minimum mu R1 and mu R2 for all Y belongs to R2 and overall maximum. So first we will find the minimum value of mu R1 x1 and mu R2 yz for the element xz, then we will find the maximum. We are defined one relations R, which is 0.5, 0.1, 0.2, 0.9, 0.8, 0.6. S is 0.6, 0.4, 0.7, 0.5, 0.8, 0.9. So that this is the x1, x2, x3. This is y1, y2. This is y1, y2. This is z1, Z2, Z3. It is just like, so T equal to R compose S. So here we will get X and Z. So it is X1, X2, X3. You can write it Z1, Z2, Z3. Now how to find? Just like a matrix, so it is first row, first column. So first to find the minimum of, you need to find maximum and minimum. Okay. So minimum of each element of y. So minimum of 0.5 and 0.6, minimum of 0.1 and 0.5. So minimum of 0.1, 0.5, then it is 0.1. So maximum is 0.5. So here we will get 0.5. Row first column. Then first row second column. So minimum 0.5 and 0.4, 0.4, 0.1. Minimum is 0.1. So that is 0.4. Similarly, 0.5, 0.7. Minimum is 0.5 and 0.1. You will get 0.2, 0.5. So maximum is 0.5. Then here we will get 0.2 row second column. Minimum is 0.2, then 0.8, so it is 0.8. Similarly, minimum is 0.2, 0.9, so it is 0.9. 0.8, 0.6, so you will get it third row first column 0.6, 0.5, so it is 0. Maximum is 0.6, 0.8, 0.4, 0.4 and 0.6, so it is 0.6 again. Then 0.8, minimum is 0.7, 0.6, so maximum 0.7. So that is the max mean compositions. So in this class, operations on Krebs relations, operations on Krebs relations, then max mean compositions, then we have understood fuzzy relations, operations on fuzzy relations, on fuzzy relations, and max mean compositions. Define any two fuzzy relations R and S. Try to find R union S, R intersection S at max mean compositions T equal to R compose X. So these are the reference of today's class. Thank you.